All right, let's dive into a really fascinating and honestly, a fundamental problem that sits right at the heart of quantum mechanics. We're going to explore what happens when the most powerful equations physicists have, well, when they just become impossible to solve.
So what do you do when the master equation of reality itself, the Schrödinger equation, just hits a brick wall? Because for most real-world problems, it is literally impossible to solve exactly. I mean, do you just give up? No way. This is where physics gets really, really clever.
Okay, so let's talk about this impossible problem. You see, the Schrödinger equation is supposed to be the rule book for the entire quantum world. It describes everything at the subatomic level. But, and this is a huge but, we can only get a perfect, exact solution for the absolute simplest cases, like a single particle stuck in a box.
But for pretty much everything else, complex atoms, molecules, the very materials that make up you, me, and everything around us, a perfect, exact answer is just mathematically out of reach. So this fundamental equation of reality is right there staring us in the face, but the perfect solution is just beyond our grasp.
So what's the move? How do physicists get anything done? Well, they approximate. And this is such a key point. Approximation in physics isn't about settling or being wrong. It's about having this amazing toolkit of clever methods to get incredibly close to the true answer. It's really an art form. So let's look at two of the most powerful tools in that kit.
First up is a method we could call the educated guess. Its formal name is the variational method. And the idea is actually pretty simple. You start by making a smart, physically inspired guess about what the solution, the system's wave function, should look like.
And here is the secret sauce that makes the whole thing work. There's this beautiful mathematical guarantee called the variational principle. It basically says that the average energy of any guess you make will always be higher than or equal to the true lowest energy, the ground state. So think about that. You can guess too high, but you can never, ever guess too low. It gives you a floor, a concrete place to start from.
So the game plan looks like this. First, you pick a guess, a trial wave function that has some adjustable knobs built into it. We call them parameters. Step 2, you calculate the average energy for that guess. Then, for step 3, you start turning those knobs, tweaking the parameters, trying to find the combination that makes the energy as low as you can possibly get it. And finally, that lowest energy you find, that's your best estimate. It's a guaranteed upper limit for the true ground state energy.
R. Shankar puts it perfectly in the book. He says the name of the game is finding the lowest upper bound for a given amount of work. It's just a very practical, efficient way of thinking. How can we get the best possible answer with a reasonable amount of effort?
And here's what really makes this method so powerful. Even if your guess for that wave function is a little bit off, it's not perfect, the error you get in your energy calculation is dramatically smaller. So you can have a pretty decent guess for the wave function and still get a remarkably accurate estimate for the energy. It's an incredibly forgiving and robust method.
Okay, so the variational method is great for finding the lowest energy state. But what if you don't care about the lowest energy? What about the higher energy states? Well, that's where our second tool comes in, the semiclassical view, or what's known as the WKB method. And this tackles the problem from a totally different angle.
The whole idea here is completely different. The WKB method is built for situations where the potential energy that a particle is feeling changes really, really slowly. Imagine you're in a tiny boat on a very long, gentle ocean swell. Yeah, the water level is changing, but it's happening so gradually that from your point of view, right where you are, the surface looks pretty much flat. That's the core idea.
And this slide really makes that difference crystal clear. On the left, if the potential is constant, a particle just behaves like a perfect, repeating wave with a single constant wavelength. But on the right, in a slowly changing potential, the particle still acts like a wave locally in any one spot, but its wavelength gradually stretches out or squeezes together as it moves through those different energy regions. So, what the WKB approximation does is it treats the wave function like it's a plane wave, but one where the momentum actually changes depending on its location. It's kind of like taking a whole bunch of local snapshots. Right here it looks like this, over there it looks like that, and then cleverly stitching them all together to build the complete picture. It's a beautiful way to connect the classical idea of changing speed with the quantum idea of a wave. And get this, here's something amazing that just falls right out of this method. For what we call bound states, think of an electron trapped inside an atom, the WKB method naturally gives you energy quantization. The math just shows you that to have a stable, self-consistent wave, only very specific, discrete energy levels are even allowed. So this semi-classical method ends up predicting one of the most deeply quantum rules there is. So, let's pull this all together now.
What we really have is a tale of two very different tools. And the real skill of a physicist isn't just about picking a favorite, but knowing exactly which tool to pull out of the toolbox for which job. And this table just sums it all up perfectly, doesn't it? The variational method is your go-to for nailing down the lowest energy state, the ground state. The WKB method, on the other hand, really shines for high-energy states, where things start to behave a little bit more like classical physics. They're based on totally different ideas, but they complement each other beautifully.
So if there's one key takeaway, it's this. One method works from the bottom up, pinpointing the lowest energy level, while the other works from the top down, tackling those higher energy states. And together, they give physicists a way to map out the entire energy landscape of a system, even when they can't solve the master equation perfectly.
And that really brings us full circle. The art of approximation isn't some minor footnote in quantum mechanics. It's absolutely essential. It's how you take these pure, beautiful principles and actually apply them to the real world.
And that's maybe the most important thing to remember from all of this. Approximation is not a compromise. It's not a failure. It is the vital bridge that connects the clean, elegant world of pure theory to the messy, complicated, and amazing universe that we actually live in.
Which, of course, leaves us with one last, kind of mind-bending question to think about. If our best, most accurate models of reality are built on this foundation of clever approximations and strategic guessing, what does that really tell us about the nature of scientific truth itself?